Okay, let me see how this is going to work today. Okay. So today we start talking about post-hoc analysis. This is actually the last set of new material before the first exam. So really the first half of this semester really has been everything about one-way ANOVA, what it is, how do we do it by hand, how do we do it in SPSS. Last week we talked about the assumptions, and this week we talk about the post-hoc analysis. So after we get through today, we'll be ready for exam number 1. Everything on homework 3 covers only things from this lecture, so the post-hoc analysis. And I'm pretty sure that we'll get through it today. So next week will be complete review, and I'll talk a little bit more about that at the end of class. So this is the outline, and we can kind of view this lecture in 3 sections. So we're going to talk overview about contrast, first of all, and then we'll talk about how to control the errors and how to do these in SPSS. And then we'll talk about multiple comparisons, mostly in SPSS, and then finish up with trend analysis. So between one of those blocks, we'll have a break. If I get to going and you need a break, then feel free to stop me. We are once again going to work on the capping and comprehension data set because we've looked at it. Last week we looked at the assumptions of it. We made a conclusion that yes, there are significant differences in the comprehension score for our different capping groups. But what is our primary conclusion after a one-way ANOVA? That a difference exists, that at least one group is different from the others. And when we evaluate this F from ANOVA, we call this the omnibus, kind of overall ANOVA. That's the omnibus F. And the only conclusion that we have from that is there is an effect and at least one group mean differs. But now we want to know which ones. So what may be some other now follow-up questions? And maybe I'll stop here and say we only do post-hoc analyses if the omnibus F there is significant. If it is significant, that tells us, okay, now we can go dig a little deeper, figure out what groups are different and what groups aren't different. But if the omnibus overall F says that there's no difference overall across these 4 groups, there's no use in proceeding to see if there are differences among 2 of the groups or subsets of the groups or so on and so forth. Does that make sense? Okay. So what might be some follow-up questions after we know, okay, there is an effect somewhere? What may be your next questions?
Which 2 groups are different?
Okay, which 2 groups are different? So is the 0 different from 30? We could compare 060, 090. We could also compare 3060, 3090, and the 60 group to the 90 group. We could look at all of the pairs. What else?
What extent?
We won't ask to what extent. We'll simply ask yes or no questions. Yeah, so to what extent would be an additional measure like effect size? Effect size would tell us to what extent. Yeah.
Which direction?
Which direction? Effect size would also tell us which direction. And some of our tests would tell us that, but we're kind of interested in a more global look instead of specifically. So once one of these 6 we see that they are different, then we could ask. So that might be a post-hoc kind of thing. What else?
thinking like which one are similar, for instance, or not?
So asking are they similar is kind of the same thing as asking, are they different? I don't only have to look at 2 groups. What might be a question that involves more than 2 groups? It can be all or it can be none.
Which 3 groups?
Which 3 groups what?
Different? Or
Okay, so which ones do you want to look at?
the 0, 30, and 60?
Okay, so are the 0, 30, and 60 groups different? That would be an adequate post-hoc test because it's looking at not an overall global, are they at least one different, but it's looking at a subset of them. Give me one more.
Do you just do one group, like it's 0 different?
Yes. I'll say, does having some amount of caffeine have an effect? So this would be like the 0 versus this grouping of 30, 60, 90. Yeah, does that make sense? Good. So you see, we can put together any pair of groups and compare them. We can put together any subset. We can compare one to a subset of another. There's a lot of different combinations that we could look at in your post hoc analysis. And so we can call these in under different subheadings of types of tests. So for the omnibus ANOVA, that global ANOVA, the full hypothesis addresses equality across all levels of the variable. So again, that was that initial one-way ANOVA where we got that single F value. Partial hypotheses address the equality of means between or across a subset of levels of the variable. So the first kind of partial hypotheses that we'll talk about are pairwise hypotheses. And these assess the equality of 2 group means. So look back at our questions. Are any of our questions pairwise? Do they involve only 2 groups? Yeah, which ones? The ones on the top, yes. So we would say that this set is pairwise because they only involve 2 groups. Is 0, the comprehension in the 0 group equal to the comprehension in the 30 group? What about the 0 group to the 90 group? All of those, so this is 1, 2, 3, 4, 5, 6 different pairwise comparisons. And actually, when we do pairwise comparisons, there are always P times P minus 1 divided by 2 total pairwise comparisons. So how many groups did we have in our comprehension example? 4, so P was 4. What is 4 times 4 minus 1 over 2? 6. And how many pairwise comparisons did we have? 6. So anytime you're doing pairwise comparisons and you wonder, well, how many are there going to be? We can just use this little formula to determine how many pairwise comparisons there would be in any study. And again, that would be comparing 0 to 30, 0 to 60, 0 to 90, et cetera, et cetera. So to write the post hoc hypothesis, specifically the null hypothesis, what would the first null hypothesis be comparing the 0 and 30 group?
equal.
What equals?
So 0 does mu of 0 milligrams equal mu of 30 milligrams.
Good. What would this one be?
So the mu of 0.
Yeah, 30.
30.
Oh, sorry.
It's okay.
Oh, I thought you were in the same.
So mu of 30 equal to
Yes.
mu of 60. Good. So we could write a null hypothesis for each of these partial pairwise hypotheses. We may also have some that are called non-pairwise that assess the relationship between more than two, but maybe not all group means. So we'll go back. The last two questions are non-pairwise. This first one here involves only the 30, 60, 90 groups. So it's a non-pairwise because it's more than just two groups, is one equal the other, but it doesn't contain all of the groups, does it? No. Even this second one, we look at and compare all of the groups, 0, 30, 60, 90, but we're not evaluating are all of them equal. We're asking, is one of them equal to the combination of the others, right? So those are considered non-pairwise. So here's one. It's that second one that we had written. Is the average reading comprehension from those receiving some amount of caffeine, so this is the 30, 60, or 90 groups, different from those receiving no caffeine? What would the null hypothesis be for that one?
Is mu of 0.
Okay, mu of 0.
Would be equal to all of them.
Equal to all of them. Okay, I'll just go ahead and write them. Mu 30, mu 60, mu 90. But what combination of them? What's a way to mathematically combine those overall? Average. Plus, and divide by 3. Good. So we're looking at the 0 group compared collectively to the 30, 60, 90 groups. Very good. Any questions so far? So for any partial hypothesis, we have a corresponding partial research question. These partial hypotheses, yes.
So what would you call that group? Would you just say, like, if you wrote something up, would you say that, like, because it's like creating another like sample in a way.
Kind of.
You know?
Instead of just having this.
That's okay?
Yeah.
Okay, go on.
Yeah. In a post-hoc sense, yes, it's okay. A contrast or a contrast coefficient, these are the numeric values of the coefficients on each group mean of the null hypothesis, specifically when it is equal to 0. So think about this being a null hypothesis. And if we set this equal to 0, what would the coefficient be on each of those group means? Those are going to be our contrast coefficients, and they're important. So these are the 3 assumptions or characteristics of these contrast coefficients. The first one is that every group mean has a coefficient. The next one is that at least one coefficient does not equal 0. And the last one is that the sum of all of the coefficients does equal 0, which implies that this contrast is valid. So sometimes we'll look at a contrast, we'll look at their coefficients, and we'll determine, is that a valid contrast? It only is if those coefficients add up to 0.
Well, I didn't understand that at all.
Let me go on
Okay.
and do the examples, and then if you still don't understand, I'll come back to this one. Sometimes it makes more sense when we actually do the application for it. So let's look at this first question. Is the average reading comprehension significantly different from groups receiving 0 milligrams to those receiving 60 milligrams? Is this pairwise or non-pairwise? Pairwise? Uh-huh. What is the null hypothesis that we're addressing here? Mu of 0
equals mu of 60.
Good. Mu sub 0 equals mu sub 60. Now that's our null hypothesis. My goal is determine, well, what are the coefficients of this hypothesis, or the coefficients of that contrast? In order to determine that, we have to first set the hypothesis equal to 0. How are we going to do that? Which one?
0 minus mu 60.
Okay, I heard mu 0 minus mu 60 equals 0. We're just taking 60 to the other side. Good. Okay, the other assumption was that every group mean is represented in that equation. Do I see every group mean within my study? Are all of them, which ones aren't there? Mu 30 and mu 60. How can I put those in here but not let them affect the equation?
Add and subtract.
Say that again.
Add and subtract, for example, mu 30.
If I add it and then subtract,
Other, both sides of the equation.
but I still want the right side to equal 0. Divide them. What do you mean by that?
So we are thinking they are the same number. They are equal. That's mu of 30 equals mu of 90.
That's what we're going to test.
We can multiply and divide each of
Multiply
them.
by 0.
Multiply them by 0. Yeah. Okay. So I can say mu 0 minus mu 60 plus 0 times mu 30 plus 0 times mu 90. Did I change the formula at all? The equation? No. Are all of my means represented? Yeah. Now the last step is I'm going to write those groups in the proper order in which they are in our study. So how could I change that? Rearrange it a little bit.
Mu of 0
Okay, mu 0
plus 0 times mu 30
No. Oops.
minus mu 60
Good. Now, I have every group mean. At least one of them is not 0. Now let's see if the sum of the coefficients equals 0. What is the coefficient on mu sub 0? What's the number out here? 1. What is the coefficient on mu 30? What is the coefficient on 60? -1. Very good. And what about on 90? 0. So is 1, 0, minus 1, 0. Do those add up to 0? Yes, so it's valid. And the coefficients are 1, 0, minus 1, 0. So these contrast coefficients are the numeric values of the coefficients on each group mean of the null hypothesis when it is set to 0. So here I have a null hypothesis set to 0, and the coefficients on each of those group means are the coefficients of the contrast. Let's do another one, okay? We'll get some practice on these, and then I'll let you do some by yourself. Okay, is the average reading comprehension from those receiving some amount of caffeine different from those receiving no caffeine? So that was the one that we talked about earlier. That's this hypothesis right here, correct? Okay, so I'll rewrite that one, and we'll work with it. I have H naught mu sub 0 equals mu 30 plus mu 60 plus mu 90 over 3. Okay. So set the hypothesis equal to 0. Somebody tell me what to do.
Mu 0 minus
Mu sub 0 minus
mu 30 plus mu 60 plus mu 90 3
Good. Everybody good there? We just subtracted that one to the other side. Okay, now we have a little bit of a problem because there's not a single coefficient on the 30, 60, 90. We need each of those group means to have their own coefficient. So how can I do that? Okay, so we'll see mu sub 0 minus 1/3 mu 30 plus, got ahead of myself, plus 1/3 mu 60 plus 1/3 mu 90 equals 0. Okay, we're closer. Right now, those three are still kind of stuck together.
I multiply it by 3.
All of it by -1? Or just part of it? Yeah, this is like some foiling, remember? Some distribution. What are we doing? This is not algebra. I know. Yes, we need to distribute this negative into the parentheses. So we'll have mu sub 0 minus 1/3 mu 30 minus 1/3 mu 60 minus 1/3 mu 90 equals 0. Have I included all of my group means? Yeah. Now what is the coefficient on mu 0?
1.
On 30?
1/3.
Negative 1/3. On 60? And on 90? Yes. So as it stands, I see 1 minus 1/3 minus 1/3 minus 1/3. Do they add up to 0? Good job. I heard at one point somebody, maybe you don't like fractions. I understand that. Not too fond of them, but I'll deal with them. Maybe in the step right here. Let me take this one over here. How could I have gotten rid of that fraction there? Multiply through by 3. That would have, if we multiply through by 3, that would have given us 3 mu 0 minus mu 30 plus mu 60 plus mu 90. And then distribute that negative sign. 3 mu 0 minus mu 30 minus mu 60 minus mu 90 equals 0. In this case, what are my coefficients? Minus 1.
Minus 1. Minus 1.
Good. 3 minus 1 minus 1 minus 1. So we see here that there are two different sets of contrast coefficient, but they're actually equivalent. What do you notice about these two sets? The sum of the values equals 0 in both of them. How could I go from one to the other even without all the steps that I put up there?
First one by 3.
Okay, so this first one that we got here, if we would just take these coefficients, multiply them all by 3, then I would get this second set. Yeah. So if the values are equivalent proportionally, we can convert or transform from one set of coefficients to another just by multiplying through by different values. So let me ask you, what about minus 3, 1, 1, 1? Is that equivalent to those? What did I do? I took this one and did what to it? Multiplied it all by negative 1. That's equivalent. What about, let's see, 15 minus 5 minus 5 minus 5? Is that the same? Yeah. What did I do? I took this last one and multiplied by 5. So even back here, instead of 1, 0, minus 1, 0, what are some equivalent sets of contrasts? Just give me some other examples.
3, 0, negative 3, 0.
3, 0, negative 3, 0. Good. What else?
1, 0, 1, 0.
Good. Negative 1, 0, 1, 0. So there's a plethora of equivalent sets of components or coefficients that are the same as the first one that we derived. So if we're doing these examples and maybe you and your neighbor don't get the exact same thing, that's okay. Maybe one of you gets 1, 0, minus 1, 0, and the other one got negative 1, 0, 1, 0. Equivalent though, okay? So I take either one of those whenever we start doing these on our own. A table of contrast is just the set of coefficients for a set of hypotheses. So I have hypothesis 1 and 2. Those are one example of the various coefficients. So here I have 0. Oh, sorry. In the first hypothesis, 1, 0, minus 1, 0. And in the second, minus 1, 1/3, 1/3, 1/3. So notice at least one coefficient does not equal 0 for each of those. And for both of them, the sum of their coefficients equals 0. So they are valid. Now let's talk about sets of contrasts being orthogonal. Orthogonal contrasts are those that are mutually non-redundant. They each give us unique information about the relationship among our groups. So though an infinite number of non-pairwise contrasts could be constructed, we come up with a lot, each one can be broken down into a linear combination of orthogonal contrast. And specifically, there are p-1 contrasts in an orthogonal set. So in our caffeine example with 4 groups, what's p-1? 3. So we could derive 3 hypotheses or contrasts. And if those 3 were orthogonal, then those 3 alone would give us everything we needed to know about the relationship among our groups. We wouldn't need any more. 2 contrasts are orthogonal if the sum of the product of corresponding coefficients equals 0. So let's see, are these 2 hypotheses orthogonal? We need to calculate the product of corresponding coefficients. Corresponding coefficients are coefficients on the same group mean. So what is 1 times -1? What is 0 times 1/3?
0.
What is -1 times 1/3? And what is 0 times 1/3? 0. So that is the product of corresponding coefficients. Now if we take and add those together, -1 plus 0 plus -1/3 plus 0, does that equal 0? No. So these are not orthogonal. Is that to say that they're wrong or they're incorrect or they're invalid? No, not at all. It's just a characteristic of pairs. They may or may not be orthogonal. So let's do some more practice with these determining contrast coefficients. Are they valid? Are they orthogonal? So I've given you 3 more questions, post hoc research questions. For each of these, generate the null hypothesis. For each of these, determine the coefficients of those contrasts. And then for each of them, determine if they're valid. And for each pair of hypotheses, so 1 and 2, 2 and 3, and 1 and 3, if this is 1, 2, and 3, determine if they are orthogonal. So do this with your neighbor. And like I said, if you don't get the exact same coefficient value, as long as they're same proportionally, that's okay. You can use the next slide also as a guide for you as you are working through this.
Yes. Just doing it. I was doing extra listening, sorry. Yeah.
So it is for level one.
Yeah. That's what my also. Oh, you're my numbers of that, so this.
Okay, the second one.
Second one is mu of 30
You're pretty good.
equal to the average of mu of 60 plus mu of 90 divided by 2. Equals
So there's only four.
And then we do, there is minus one.
I'll,
Multiplying by.
Yeah.
Okay, the third one.
Mu of 60 equals to mu of 90.
so we add mu.
Oh,
So we should add mu of 30.
Oh, we're multiplying.
0.
That's
We're
right.
multiplying.
0 mu of 0. Equals 0 mu of 30. Plus mu of 60 equals minus.
Yeah.
Okay. That's it.
Right?
all the time.
It's 2.
Oh, yeah, the balance.
And here too.
Yeah.
Zero.
Same thing,
About 3 more minutes, we'll talk about it. 4:15.
Yeah, except for the question. Question 5. Right? What did you do?
Are you sure about these numbers?
Oh, no, I like to write it down so I understand it.
There is -1.
Now I know what I have. Oh, here. So, you have to use basically the words to find measure, the 2 such find measures.
I get that too, so. Okay, so let's do these together. The first question is the mean of the 60 group significantly different from the average of the 30 and 90 groups? So for the first one, what is your null hypothesis? Good. Oh. Good. Or yeah, you could say 1/2 mu 30 plus 1/2 mu 90. You could go ahead and say that in the beginning, and that's perfectly fine. Yeah. What are your contrast coefficients? Again, there could be different interpretations, but what did someone get for the contrast coefficient for hypothesis 1? 0 on mu 0. -1 on mu 30. 2 on mu 60. -1 on mu 90. Good. Okay, does somebody else have a different version? Anybody else do something different?
I did 1 -1/2, -1/2 0.
1. Are they in order?
No.
Okay, so which one is your coefficient on mu 0?
0.
Okay, which one is on mu 30?
-1/2.
Okay, mu 60
1
and mu 90.
0/2.
There we go. Yeah, so there's another version. Anybody else do something different? Okay, what about the second null hypothesis? It reads, is the mean of the 30 groups significantly different from the average of the 60 and 90 groups? What is your null hypothesis?
of 30 equals mu of 60 plus mu of 90 divided by 2.
Okay. And what are your contrast coefficients for that one? What's on mu sub 0? 0. What about mu 30? Mu 60? And mu 90? I like that. Anybody do something different? Or you're not sure if your different one is equivalent to that one? We could all have essentially a different one. Okay, and the last one is, are the 60 and 90 milligram groups significantly different? What is that null hypothesis?
Mu of 60 plus mu of 90.
Good, that's a short one. That one's the what one? Pairwise, yes. And what do you get for the contrast coefficients? What did you put on mu 0?
0,
On 30,
0,
60,
1,
and 90.
1.
And you could have done -1, then 1, or 2 minus 2, so on and so forth. So are these sets valid? So the first thing, validity has to do with each one. So hypothesis 1, hypothesis 2, and hypothesis 3. For hypothesis 1, does the sum of these values equal 0?
Yes.
For hypothesis 2, the sum, does it equal 0? And what about hypothesis 3?
Yes.
Yes. Okay. Now for orthogonality, for this one, we need to look at 1 versus, or 1 and 2, 1 and 3, and then 2 and 3. We need to look at all pairs of the different hypotheses. Okay. So first, let's look at, let me erase these lines. First, let's look at 1 and 2. So I'm going to box that one. We're going to multiply corresponding coefficients and then add them up. Okay? So I'll look at the coefficients on mu 0. That's going to be 0 times 0. And then on the second one, I see -1 times 2. And then 2 times -1, and then -1 times -1. You see where I got those numbers that I multiplied? So I'm looking at the pairs of coefficients, multiplying those, and then adding those products together. So I have 0 plus -2 plus -2 is -4 plus 1 is, what is that? -3. Does that equal 0? No, not equal 0, not orthogonal. Okay. Let me erase those doodles.
So it's 1 by 1.
So now let's look at 1 and 3, and we'll look at, again at the pairs. So the first pair is 0 times 0 plus -1 times 0 plus 2 times 1 plus -1 times -1. What about that one? What does that equal? Two? 3? I see 0 plus 0 plus 2 plus 1 equals, okay. And does that equal 0? No, not orthogonal, okay. Now let's look at the last set. hypothesis 2 compared to hypothesis 3. We have 0 times 0 plus 2 times 0 plus minus 1 times 1 plus minus 1 times minus 1. What does that equal? 0. We finally have one. Orthogonal. So we would say that hypotheses 2 and 3 are orthogonal to us. They each give us unique information about the relationship across our 4 groups.
Can you repeat this?
Yes. So by saying that hypothesis 2 and 3 are orthogonal, we're saying that those two give us unique information. We can't get it, when we know the answer to one, it gives us no indication of the answer to the other hypothesis. But you'll notice that like hypothesis 1 and 2, they both relate to the same set of hypotheses. And the information, because they're not orthogonal, the information that we get from one, we can manipulate the other one and get similar information about the relationship. So the conclusion that we get is somewhat redundant. Again, it's okay in your study if you have non-orthogonal contrast, as long as it aligns with your research question. But it's good for you as the researcher to know if you have a set of orthogonal or a set of non-orthogonal contrasts. Okay. So controlling the type 1 error rate. With each set of analyses that we do, there is a chance of error. So even when we said the very first time we talked about ANOVA, we said, well, why not just start out with a bunch of pairwise comparisons? Why not just start with 0 compared to 30, 0 compared to 60, 0 compared to 90? What was the point of the Omnibus F ANOVA test? To see if there was an overall global difference, because in that single one test, there was a 5% chance of error. But if we do a series of pairwise tests, each of those has 5%, 5%, 5%, which compounds and expands in the overall error rate of your study. So the more tests that you perform, the more chance of an incorrect conclusion. So again, type 1 error is the probability of rejecting a true null hypothesis, and conventional levels we've seen are 0.05 and 0.01. We have to keep this in mind when we do multiple post hoc tests. So there are some formula that will help us to calculate the overall error rate when we do multiple tests. So let's say that we do a set multiple post hoc tests. Let's say we do C post hoc tests. Then the probability of making a type 1 error per contrast is alpha PC. So for all of those hypotheses that we just did, there's a 5% chance of error on the first, a 5% chance of error on the second, a 5% chance of error on the third. The probability of making a type 1 in that family of contrast is called a family-wise error rate. So if we just did all 3 of those, what would our overall chance of error be? The formula is given by 1 minus the evaluation alpha for each contrast or per contrast raised to the C power. So however many contrasts you're doing is what number goes in on the C. So in that example, we just had a set of 3 hypotheses, right? So we did 3 contrasts. Hypothetically, let's say that each one of them was done at an alpha 0.05. That's probably initially what we would have done. Well, in that set of 3 contrasts then, the overall family-wise error rate would be 1 minus 0.05 to the 3rd power. Can somebody do that calculation?
$0.14.
0.143. Did anybody else get that? Okay. So if we would, in SPSS, we just put those 3 in, we look at them, we evaluate each one at a 0.05, it doesn't imply that overall we're maintaining a 5% chance of error globally. It actually says that globally there was a 14.3% chance of error. Oh no. You don't want to do a study and then say, there's a 14.3 chance of error, 14.3 chance that you're going to say, yeah, there's a difference, when really there's not. So we need a way to maintain that global alpha. We need to maintain that 0.05 so that even when we're done, we say the overall alpha rate is 0.05. So we're going to have to decrease the alpha for each of those 3, right? We do each of those. So maybe instead of a 0.05 right here, maybe I want to do a 0.01. What happens if you get if you put in 0.01? What would this change to? What would your family-wise error rate be if instead you did 99% chance on each one?
0.03.
0.029. Oh, yeah, 0.03. Oh, so that really reduced it. Now there's a 3% chance. Well, we don't maybe want to be quite that strict with our estimate. So what number could we evaluate each of those at so that overall alpha family-wise does equal 0.05? Let's see if we can work backwards and figure out what that would be. So if instead we determine we want an overall 0.05 type 1 error rate, I'm going to put in the equation, what does the pairwise alpha rate need to be? What does that number need to be? So now we're going to have to do some algebra again. How can we solve for alpha PW? I'm sorry, PC, not PW, per contrast.
So we have to not the roots. I don't know how to say it.
Let me rewrite it over here so I have a little more room, if that's okay with you. Okay, so my question is, if we determine that we want the family-wise error rate to be 0.05, what do we need to do each alpha per contrast at to maintain that? So we don't need it to be 0.05, but we don't need so strict that it's 0.01. It's going to be somewhere in between there. How do I solve for alpha PC?
I need to take that third.
Uh-huh.
So I do it's not square root, it's the
Cube root. But we don't need to cube root all of it quite yet because I still have this piece out here. But it's close.
okay.
That'll come.
That's okay.
What should I do first?
Oh, move that one.
Okay, move the 1 over. Okay, so I'll have 0.05 minus 1 equals minus 1 minus alpha per contrast to the third. Now what?
Multiply it by minus.
Multiply it all by minus 1. So then I'll have 1 minus 0.05 equals 1 minus alpha PC to the third. Okay, now we're getting somewhere.
Q squared.
So the cube root, right? And did y'all know that if you take x squared, no, that's not how I wanted to say it. If you take the square root of x, that's the same thing as raising x to the 1/2 power. Did y'all know that? So the cube root of x is raising x to the what power? 1/3. So that's what we'll do here. Okay, so we'll say then 1 minus 0.05 to the 1/3 equals 1 minus alpha PC. And alpha PC, it's not quite by itself yet. Good. Now, put that in your calculator and let's see what you get. .017. Anybody else get that? And put this in your like now's the time to practice because it's sometimes hard to put those exponents in your calculator, especially as a fraction. And we're here to practice, so don't want you to get home and think, oh, I don't know how to do that. Raise your hand when you get it in your calculator. Okay, thank you.
Is it 1 divided by 3? Is that the way to put it?
In the exponent, So I have a little TI 30X. It's not scientific, but I have to put it in like this. I put 1 minus parenthesis 1 minus 0.05 close parenthesis, and then I have a little arrow parenthesis 1 divided by 3. And if you want, you can add a double parenthesis. So it's using that little hat, if you will. Raise your hand when you get it. Okay, good, good. Okay. Somebody else have it? Okay. Practice, and as we go through these, if you're not getting it, I can come and help you individually. So what did we just do? If a set of C post-hoc tests or contrasts or hypotheses were performed all at the same alpha per contrast rate, then the overall error rate would be alpha family-wise equals 1 minus alpha PC to the Cth power. But this tells us really how inflated our overall alpha rate is. And it's often way too high than what we want to maintain. So we determined that we could manipulate that formula a little bit to determine what each alpha should be to maintain the overall error rate. So that adjusted formula was alpha per contrast, 1 minus alpha family-wise to the 1 over C. So there were really close relationships. Even if you go back to this slide, there was a really close look between this one and this one. So right here, this was alpha per contrast, and this was our C. But down here, the 0.05 was our alpha family-wise, and the 3 was still our C, but it was 1 over 3 instead of just 3. So these are the formulas. So if I say, what is the overall family-wise error rate if you do alpha PC on C, but this one is often inflated. And we don't want an inflated type 1 error rate. We want to maintain or control the overall error rate. So this is what we should do. What we should test each contrast at to maintain an alpha family-wise. Control that overall alpha. Okay. Questions? Is it okay? Okay. So you now, on the next 4 slides, there are 4 different setups. And so for each of them, you're going to calculate the alpha family-wise and the alpha PC using these 2 formulas up here in red. And notice that each one might have a different number of groups. Some of them ask for pairwise. Some of them ask for orthogonal. So you'll figure out how many, but this is C. Whatever you put here is C in your different formula, okay? Let's do the first one together, and y'all can do the other 3 by yourself. Is that good? Okay. So here, we have a design with 4 groups, just like our caffeine group. Let's say we were to do all pairwise comparisons. How many comparisons would that be? What is 4 times 4 minus 1 over 2? 6, okay? So in the set of all 6 pairwise comparisons, what is the probability of making a type 1 error rate if we do all of them at an alpha 0.05? So that's going to be 1 minus 0.05 to the what power? 6th power. Calculate that. What'd you get? 0.265. Wow. Potentially 26% error rate if you did all of those essentially t-tests, pairwise comparison. That's way too high. We can't do that. So here, what should we do per contrast alpha to maintain the family-wise at an alpha 0.05 in 6 contrast? So my exponent is now 1 over 6. What did you get for this?
0.009.
0.009. Yeah. So we're really going to have to look at each of those individually on really small alpha so that we can maintain the overall error rate of 0.05. Good. Yes.
So when in SPSS that you do like a post hoc analysis, instead of putting the 0.05, you would put 0.009 to keep that.
Each different test is different.
Okay.
So when I talk about an SPSS, I'll tell you which ones we have to look at and which ones we don't. Yeah. Okay, so the next 3 slides now. Why don't you guys do those on your own?
Did you calculate this 10?
It's 1 minus 0.1 is 0.99, right? And then
One minus.
Yes. Yes.
we want to keep as a point and then
One minus.
Oh, I'm doing it. That's why.
Why not? It's 4. So P is equals 5. What's the last? For this calculate. So we have this.
Yes.
Listen about the project we have to do, and we will need to have some literature review or something like that, just for honors.
Yeah. Yeah, we follow that rubric, straightforward.
Oh, okay.
Okay, I'll give you 2 more minutes.
I do, I have. At least you know how to do it. I know.
For the research, you mean? For the project? I think it's after the exam. So,
So we still don't. I am still confused with the orthogonal, like,
Orthogonal?
for instance, like the number of orthogonal, I'm sorry, I'm just like, I just follow the formula, but I have no idea what that means. The pairwise I understand, but
So 2 contrasts may be orthogonal, they may not be orthogonal. If they're orthogonal, that means that they each give us unique information about the relationship among our groups. If they're not orthogonal, that means, in a sense, one of them is redundant because information that we get from one, we could also get from the other.
so when it's redundant, it's not orthogonal, or it is orthogonal?
Orthogonal is non-redundant.
Okay.
Yeah. Okay, so I have the answers up here for you to check through. The next one, we had 4 groups, so there are 3 orthogonal contrasts in that set. We have a family-wise error rate here. That would be 0.143, but that's too high. In order to control it, we want to do each of the pairwise, or each of the contrasts, sorry, at 0.017. Did y'all get that? Okay. So the next one, we have 5 groups. So there are 10 pairwise, 10 pairwise comparisons. We want, in this one, we're doing things at an alpha 0.01 rather than 0.05. So the family-wise error rate for the 10 pairwise, oops, that doesn't look right.
Yeah, it is right.
Oh, okay. So, because we're doing each of them in a smaller one. Okay, there we go. So overall, there would be about a 9.6% error rate, but that's still too high, especially when globally we're trying to maintain 0.01. So we should do each of those at a 0.001. And then in the last one, if we had 5 groups, there would be a set of 4 orthogonal contrasts. Again, looking at it with a 99% error rate, if we did all 4 of those at this alpha PC, we would have an overall error rate of 3.9%. But to maintain that global alpha, we should do each one at 0.003. Okay. Questions on that? We're good? Let me show you then how to test these in SPSS. So I brought up the comprehension and caffeine data set. And specifically what we are going to look at is putting in the, let's see, table. Let's reference back to this one here, slide 13. And we have our table of coefficients here in the middle. So in SPSS, if you want to follow along with the instructions here, we're going to, let's see, slide 22. Click Analyze, Compare Means, and One-Way ANOVA, just like you're doing the original One-Way ANOVA. And then we will put comprehension score as the dependent variable and caffeine group as the factor. And then notice that we have this option of contrast. So that's where we're going to put in our contrast coefficients. It looks like here, I just want you to do that first, those first 2 that we did together. So is the average reading comprehension different from the 0 and the 60 group? So our coefficients were 1, 0, -1, and 0. To put those in here for contrast number 1, we'll do 1, add, 0, add, -1, add, and 0, add. That's the first contrast. Notice that it keeps track of if these are valid or not. And then continue, and we'll put in, next, Click next, and you'll go to contrast number 2. So for this one, we have the contrast coefficients for comparing 0 to the average of all the others. Those coefficients are 3, add, -1, -1, and -1. Now click continue. Were y'all able to put those coefficients in for all of them? Okay. So if you click OK, now we get output that still has the ANOVA table. The ANOVA table did not change at all. But we also then get the contrast coefficients table that we just entered, and we get the contrast tests. Did everyone get those 2 output? Okay, so I'll talk about them on this slide here. First off, in this set of 2 contrasts, what should each of the contrasts be evaluated at in order to control the family-wise error rate to 0.05? So again, we have 2 contrasts. What is 1 minus 0.05 to the 1/2? What do we need to evaluate each of these at? What's our alpha family-wise here, or our alpha PC here that we need to use to control? You confused? Okay. What are we using here? Point what? 0.05? No? Okay, remember what we're doing here. Just like this. Right here, we said we were doing 4 comparisons and we wanted to maintain the overall alpha to 0.01 for that set of 4 contrasts. We did this formula. We said, okay, we're going to do each of them at 0.003. So what we're doing here, we have 2 contrasts, so C equals 2, but I want to maintain the family-wise error rate to 0.05 for that set of 2 contrasts. So what should we evaluate each one of them at? 0.025. Somebody else? I need some participation here.
Why would we be evaluating it at 0.025? Are we comparing it? No, I'm confused.
Okay, ask me your question. What is your question?
Oh, what, she said 0.025, I don't get why it's 0.025.
Did you do this mathematically you don't understand or conceptually?
Oh, that's mathematically.
Yes.
Oh, okay. I understand. Like what?
Did anybody else get 0.025? Okay. So we should evaluate each of these at 0.025. Did we meet Levine's test for homogeneity of variance? Yes, we did. So we're going to assume equal variances, and we'll just look at this top portion here. So for the first contrast, is the 0 milligram group equal to the 60 milligram group? What does our p-value tell us in relation to our alpha 0.025? It is different, so we're going to reject the null hypothesis. This is evaluating it like a t-test because it kind of is like an independent t-test for these 2 groups. So we're using a t-test statistic, and what were the degrees of freedom? 16, and what is the test statistic value? Minus 7.746, and we'll say P is less than 0.025. Yeah. So that compared 0 and 60. That says that this group mean is significantly different from that group mean. And it looks like it on the graph. Now the next one was, is the 0 milligram group significantly different from this set of the 30, 60, 90 group? What does this one tell us? How do we evaluate contrast 2? How many people say, and raise your hand, reject the null hypothesis? How many people say retain the null hypothesis? Okay, I need everybody to participate. How many people say for contrast 2, reject the null hypothesis? Retain the null hypothesis? Please be honest with me. I don't understand. I'm lost and I'm tired and I'm ready for a break. Thank you for your honesty. We'll get through this and I promise we'll go on a break. Okay, so how do we determine it? How do we make our conclusion if we should reject or retain the null? The p-value. What is the p-value? 0.000. So the p-value is what to my alpha? It's less than. And if p is less than alpha, then we Reject, there we go. Okay, here we go. Reject the null. I know. T have how many degrees of freedom? 16. The test statistic is negative 6.325. Here we go. The P is less than 0.25. Good. Yes.
How do you understand that each one is, contrast number 2? So this hypothesis.
Because we told it by our contrast coefficients that was contrast 2. Each one of those, 1 and 2, corresponds to number 1 and number 2. And that's how we put it in SPSS. Yes.
Go back one slide.
Whoop.
So, I don't understand the first bullet. If we're trying to correct for type 1 error rate, we only report the second bullet point?
No, we can report both of them because we controlled the overall type 1 error rate.
And the second one?
In both of them, we controlled the type 1. We said P was less than the controlled alpha for both of them.
Isn't that pairwise? Are we comparing 1 versus 2 in both?
No.
That's
the first one is comparing the 0 and the 60 group. The second one is comparing the 0 group with the set of 30, 60, 90.
Oh, I see.
Yeah. Yes.
So for the contrast test, the p-value is 0.25 instead of 0.05, and that's why we are rejecting it. If we didn't do this contrast, wouldn't it be 0.05? The p-value or the alpha?
Even if we weren't controlling, if we were using alpha 0.05, would we make any different conclusions?
Oh,
No, we wouldn't. But as a researcher, we may be making more errors than what we think we are.
Okay.
So by using 0.025 as our evaluation criteria for post-hoc analysis, we are being reliable so that overall, when we say alpha was 0.05, it's still overall globally 0.05.
Okay.
Did I answer your question? A little
I
bit.
can figure it out.
Okay, you can ask again if you want.
I mean, it's like if the significance would have been, 0.026, then we would have retained the null.
Right. Mm-hmm.
And we need to calculate the new alpha, or there's an option in the SPSS that can calculate that.
Some of them will, but if you do it this way, where you have a predefined contrast that you're plugging in just like we did, then you as the researcher need to control it yourself. Other questions?
So if the significance came out as 0.2026, would we still be rejecting the null, or would that be actually?
Yep. So think about this. It is possible that omnibus alpha 0.05 reject the null. But when we do this post hoc analysis, it's possible both of them could have been 0.026. Right? Yeah, and mathematically that can happen. And we can say, yes, at least one group mean is different, but there is no difference between 0 and 60, and there is no difference in 0 and this set when we provide constraints that control the type 1 error rate. And that does happen in research. Yeah. Okay. Other questions? Okay, so what time is it? It's 5:07. So you can do this in whatever order you want to. At some point, take a break. And at some point, use SPSS to evaluate these 3 hypotheses, that set of 3 hypotheses. I've already given you output, but I want to know that you can replicate it. I want to know that you can determine how we should control them and then make a conclusion for both of those. So at some point, take a break, and at some point, evaluate this in SPSS. And if you want to use the contrast, the whole number contrast coefficients, go right ahead. It won't change your results. The ones that were on slide 13 or something that we did should get the same results, okay? Okay, so maybe 10 minutes if possible, 12, maybe 13 minutes, okay? So around 5:20, we'll talk about it.
Do we need to erase the previous contract?
Yes, you will have to remove those.
Where's this data set? Do you know where's the data set?
No. I have it in my phone.
When you have your output in SPSS, I would like to see it.
I have it.
Okay. Very good. Very good. Very good. Okay. I'll wait till everybody gets back and then we will keep going. Okay, so did everyone also agree that we should do each of these at an alpha 0.017? Because we have 3 of them, good. Okay, so the first hypothesis we evaluate comparing the 60 group to the combination of 30 and 90. Are those significantly different? Yes, so we'll reject the null. We would say that T with how many degrees of freedom? 16 equals what value? 4.472, and P is less than 0.017. Very good. Okay, what about the second one, comparing the 30 group to the combination of 60 and 90? Is that one significantly different? So we retain the null hypothesis. T with 16 degrees of freedom equals what value? Minus 1.491, and P is greater than 0.017. And if we look at that, we're comparing this 30 group to the combination of the 60 and 90. Does it look like there's a big difference there? Not really. Whereas the previous one, we were comparing the 60 group to the 30 and 90, and we see some differences on the y-axis between those two groups. Okay, the last one just compares the 60 and 90 groups. So this one and this one. Is that significantly different? Yes. So here we reject the null hypothesis. T, again with 16 degrees of freedom, equals what value?
4.303.
Very good. And P is less than 0.017. Very good. So the contrast feature in SPSS allows you to evaluate those planned contrasts where you're usually looking at a subgroup of contrast or non-pairwise comparisons. There are a lot of built-in, so I'll just kind of give you all a little breather. I'm thinking we might need to stop here, if that's okay. Next week is only review. So next week we'll finish trend analysis plus do a review. Is that okay with y'all? I'm not thinking we would make it. Okay. Yeah. So we'll breathe. We're just going to coast on out of here with SPSS. When you use SPSS, if you click on the post hoc, you will get all of these options. Those are a lot of different options in SPSS. Which one or ones are you familiar with? We've heard of Shafay. We've definitely heard of the Tukey test. The LSD, least significant difference. Maybe some of us have or some of us have. Which one's the most popular? Ooh, I would say probably Tukey, but some would use the Bonferroni quite often. This is again in your one-way ANOVA, clicking post hoc, and then you would select one. You could select all of them. I don't recommend that. I'll talk about now which ones to choose in what different situations. So these could come under some different subcategories. First off, you see them already divided in those 4 equal variances assumed and those 4 equal variances not assumed, and there aren't quite as many options there. The ones for equal variances assumed, they differ in what kind of test they are. They also differ in the kind of output that you may or may not get. Most often, though, they're going to provide all pairwise comparisons. And they have a test of significance, a p-value, and a confidence interval. If you're doing a study that has a control group, for instance, our caffeine group, and maybe your sole intention is to compare each group with the control group, then the Dunnett test would do only those pairwise comparisons, each of the treatment groups with the control group only. Then there's this other subset that I would say is not quite as common, and these do not provide confidence intervals. So we can't determine just from these the direction of the test, like someone indicated earlier. Sometimes we want to know, is one less than or is one greater than, other than just different. So if you're wanting to know direction, then again, you would want to stick with these top categories: Bonferroni, LSD, Tukey, etc. The tests differ in how conservative or how liberal they are in their controlling of the type 1 error rates. So these SPSS will automatically provide the adjustment for alpha if that test makes that accommodation. So if you do a contrast, you have to go through the steps. What do we need to use alpha? So on and so forth. But if you're using one of these, SPSS will do it for you. So you just determine your omnibus alpha and you stick with it. You don't need to modify that at all. So recall this relationship. If the type 1 error decreases, what happens to the type 2 error? Increases. And what happens to power? It decreases. What happens if you have a type 1 error rate that's higher? Your type 2 error rate is lower and your power is higher. Yes. So here, a conservative test implies that you are less likely to make a type 1 error rate. But that decrease in the type 1 error rate also does what to your power? It decreases in power and are less likely to detect significant differences if they exist. But a more liberal test implies that you are more likely to make a type 1 error rate. The true alpha might be higher than what you specified. But an increase in a type 1 error rate also does what to your power? Increases your power, and so you are more likely to detect the differences if they exist. So by the way that these different tests control the type 1 error rate, they may or may not be more or less conservative or liberal. So that first set of pairwise comparisons, when all variances are equal, we met that assumption. And these are the ones that I would probably most often choose from because they provide a mean difference, standard error, significance, p-value, and confidence interval. So as a single step method, that's what these are. The decision of rejecting or retaining is actually based on a confidence interval. That's why it allows for a directional conclusion. So do y'all remember this from way back when? If a confidence interval contains 0, it is or it is not significant. It's not significant. But if the confidence interval does not contain 0, then it is significant. We'll still have a p-value to evaluate yes or no, but we'll also have that confidence interval to back that up and then provide further indication of directions. So I have these ordered here from least conservative, meaning most powerful, to most conservative but least powerful. So the LSD, someone was familiar with that, it tests all pairwise comparisons at the original omnibus alpha, but it doesn't control the family-wise error rate. So it would be like looking at everything, not making any modifications of alpha. So it increased that type 1 error rate, but it also is pretty powerful. If the differences are there, we will detect them with the LSD. Tukey controls the family-wise error rate so that it's equal to that of the omnibus. That's the method that I gave you to perform whenever we're doing individual contrast. You want to maintain the overall family-wise error rate. That's what Tukey does for you automatically. So again, you don't have to do any additional calculations. It will modify the alpha so that you can evaluate it to 0.05, like you would have the original F. Actually, the Tukey is only for equal sample sizes. That's all you'll see in SPSS. But it automatically will apply the Tukey-Kramer when you have unequal sample sizes. And so because it controls the family-wise error rate, and it still has some power, Tukey is often the most popular one. I'll just let you read through these other ones. Suggestions for when you have unequal sample sizes, or maybe they are very different. And then the done it specifically is when you have a control group, but it is one of the least powerful tests that we have. Questions about those? Okay. So the next two slides, I give you some formulas, and don't worry, you're not going to have to calculate anything. But I want you to see, what does SPSS do? When you tell SPSS to do a Tukey test, honestly significant difference test, it looks at the two group means that you're comparing, probably like with coefficients 1 and -1, a pairwise comparison, contrast coefficients. It subtracts those group means and then divides by some measure of error. That formula is actually very similar to the formula for an independent t-test statistic. It's a difference in means divided by the square root of the measure of error. Modifies it slightly, but I provide these three equations, again, not because I expect you to memorize them or probably ever look at them again in your life. I'm not going to ask you to recall them on the exam, but I do want you to see how closely related they are. So Tukey-Kramer, when we have unequal sample sizes, it still does the same thing essentially with a measure of error and subtraction of the group means, but it takes into account the group sizes because it knows that they're different. The Dunnett test, notice the modification here. There's a 2 in the denominator. That's the only difference in the calculation of the test statistic between the Tukey test and the Dunnett test is that the denominator also has that multiplication of 2. Other common ones, the Bonferroni, the Chaffee, the Hochberg, they all maintain that same overall structure of difference in group means on the top and some measure of error in the denominator. But they're all named after a different person because some person thought that theoretically this one might better capture the difference or that one might better capture the difference just by these slight modifications. Again, often the choice is up to you, but I would kind of use that slider. Do I need a powerful one? Or do I need a conservative one? Can I get rid of some power but be liberal? And that's up to you as the researcher. Some of the other ones that are listed, instead of single step, they're called a stepwise test. So these form groups whose means are not significantly different. So instead of, doing a pairwise this to this, this to this, this to this, it looks at them in subgroups and compares their different means. So this might be the SNK or Duncan. There are different terms for these. I honestly don't ever use these. I would most often use Bonferroni, Tukey, something like that. But they're in SPSS, and I often have students say, well, what are those other ones? What are those ones we never use? This is just a little bit information. The process of calculating them is slightly different. And then there are only 3 that are used when variances are unequal. When variances are unequal in the omnibus F, what modification do you use? What's it called? Levene's test homogeneity of variance. And if it passes, we just keep going. We look at our original F and we proceed. But if we violate Levene's test, we have to do a modification. Welch's statistic. If you use Welch's statistic, that one is significant. You want to follow up with a post-hoc test. Then you would do that with one of these 3 because these 3 also accommodate for unequal variances. The Games-Howe, the Dunnett-C, and the Dunnett's T3. So again, the differences are most often based on how conservative or how liberal these tests are. Games-Howe, an extension of the Tukey-Kramer, is the most powerful of the 3, but it's also the most liberal, higher chance of type 1 error. But it's the best choice when your populations are known to be unequal. The Dunnett, so we're kind of like power here, most powerful. The Dunnett C, less powerful than the games, more powerful than the T3, when the number of error degrees of freedom is large, or that the sample sizes are larger. And I'll put that in quotes. What is large when we're in this class? Well, probably if they're greater than 30, that tends to be a common factor for sample size in terms of large for an ANOVA test. But if the sample sizes are smaller, less than 30, then Dunnett's T3 tends to be more powerful. Both of these do control the family-wise error rate and are preferred if controlling the type error rate is important and population variances are actually believed to be similar. So that difference in population variances was just a matter of your data, a sampling error or something like that. But in the population, we may believe that they are equal. So again, I give you the formula for those just to show you that the structure is not a whole lot different. In the numerator, we have a difference of means. In the denominator, we have a square root, some measure of error or variance. But there are just ever so slight modifications. So let's do one of these in SPSS. Let's specifically do a Tukey test. So in SPSS, you can go back into your Analyze, Compare Means, and One-Way ANOVA, and then click on Post Hoc and click Tukey. Now this is going to maintain your overall family-wise error rate, which tends to be 0.05. But if you wanted a family-wise error rate of 0.01, you could modify that here in your level of significance to maintain that adjusted type 1 error. You just click Continue and OK. So then you notice you still get your ANOVA. I hadn't deleted my contrast from before. But then for the post hoc test option, we have multiple comparisons tests and this homogeneous subsets table. Did everybody get those two tables? Okay. So let's just talk through how to read those tables. So Tukey controls the alpha family-wise so that it is equal to the alpha of the omnibus. So if P is less than the omnibus alpha, then there is a difference. If P is greater than, it is not significantly different. And you actually get both comparisons twice. I don't know why they do that, but they do. So here we could compare the 0 to 30, 0 to 60, 0 to 90, 30, 60, 30, 90, and 60, 90. There we go. Okay. So those are the 6 pairwise comparisons that we are interested in. Again, we don't have to modify alpha because it does that for us already. So is the 30 and the 60 group significantly different? If we look at the p-value here, does it look significantly different there? P is what? 0.003. Is that less than or greater than alpha 0.05? Less than. So I would say yes, the 0 and the 30 are significantly different. What about the 0 and the 60 milligram group? Are those significantly different? Yes. It would make sense that if this is significantly different, then that is significantly different. Yeah. Okay, what about the 0 and the 90 milligram group? Yes, again, that one is significantly different. Now, what about the 30 and the 0? Well, notice that's the same as 0 to 30. The row looks exactly the same, except instead of positive, it's negative, negative, it's positive. So we don't have to look at that one. What about the 30 to the 60? So that one, change colors, 30 to 60. What about this group difference? Is that one significantly different? Yes. What about 30 to 90? Is that one different? No. But notice it doesn't look a whole lot different in terms of its actual value on the comprehension score. And then let's see, 60 and 90 is the only one we have left. This one here. And is that significantly different? Yes. So that's where we can look at and evaluate each of the pairwise comparisons from that multiple comparisons test. You also get another output. Some students like this one as much or more, and some people hate this box. So you can make your own choice. It doesn't matter to me. But this is a homogeneous subsets output. So group means listed in the same subset or column indicate that those groups do not have significantly different means. If group means are listed in different subsets or columns, then they do have significantly different means. So what this tells me is that overall we could create from these 4 groups, the 0, 30, 60, 90, they could be differentiated in 3 different subsets. The 0 group would be all by itself in subset number 1. In subset number 2, we would have the 90 and the 30 group. And then the third subset is only the 60 group. Okay, so now we could compare. If we're trying to compare 0 and 60, well, those are in different subgroups, so those are significantly different. Yeah.
I actually made a group on that.
Oh.
It says 30 and 90 are the same subset.
Ah, thank you, thank you, thank you. So number 2 was 30 and 90. Thank you. And this one is subgroup 3. I greatly appreciate that correction. Now, if something is in a different subgroup, then it is significantly different. So again, 0 and 30 are different, 0 and 60 are different, 0 and 90. But because 30 and 90 are in the same subgroup, same column, those are not significantly different. Again, this table and the previous table gives us the same exact conclusions, just in a different format. So use whichever one you feel most comfortable with. Or use one to verify, but sometimes looking at it in terms of subsets is helpful. So this last thing I want to show you is not something that I would do in practice. Not at all, but I just want to show you for comparison. I did all of them. I did all the different, most of them, all of the different tests. So you'll see Tukey's test, Scheffé, LSD, Bonferroni, Hochberg, Gabriel, Siddick. Okay, like I said, you wouldn't normally do all these different post-hoc tests that essentially give you the same exact results for a single study. But I do want to point out what is different. So if you chose to do the Tukey test and you were comparing the 30 and the 60 group, so that's the 30 and the 60 milligram group. Based on the Tukey test, again, when we use the automated pairwise groups in SPSS, we don't have to modify our alpha. So we're just using alpha 0.05. What is the significance level for the Tukey test to compare 30 and 60? 0.02, okay? What is it for the Shafay test? 0.03. What is it for the LSD? 0.00. What is it for Bonferroni? 0.02. So this is important because if your global alpha was a 0.01, some of these would tell you it's different and some of them wouldn't. Because some are more powerful, some are more liberal, some are more conservative. There's a different increase in type 1 or a type 2 error. So again, it's up to you as the researcher which one you choose. To an extent, I wouldn't print this off and then think, okay, I'm going to use this one because that one is significant and the other one doesn't show significance. Let some theory, that's why you're taking this class, let some theory, some knowledge, some understanding guide which one you want to choose. Maybe it's okay to be liberal. Maybe you want to increase your power. Those types of things should prompt you to use one of these tests, and then you can interpret it appropriately with appropriate evaluation of your error rates. Okay? So when you do post-hoc analyses, again, kind of putting all that we've done so far this semester together, the first thing you always want to do is to check your assumptions. You don't have to write a whole page about your assumptions and how you evaluated them. A paragraph that at least lets the reader know you checked them, these are the results, and do you need modifications? Then, what are your results to the omnibus F test? That is the overall global F. Is there at least one significantly different group mean? If so, then you proceed to the post hoc analysis. Tell us which test you did, what alpha, and provide not just this is different from that, that group is different from this, but really try to tell a story to your readers of how you're interpreting the results. So here I say that scores are significantly different from all other groups compared to those receiving no caffeine. Those receiving 30 or 90 had similar effects, and those receiving 60 resulted in the highest comprehension score. Okay. Any questions on contrast, multiple comparisons, doing this in SPSS? No? Hopefully no. Go home and practice. And then next week, we'll talk about one other type of post-hoc analysis called trend analysis. And we will review, let me just briefly tell you about how I do the review. In Brightspace, under the discussions, you'll see an exam 1 discussion. And it's anonymous, but it's also, what do they call it? I have to approve the post. So once you post it, it's not for the world to see. It'll be hidden until I see it, and then I can approve it or not approve it. But that's where if you have questions that you would like to talk about next week after we get through trend analysis, that's where I'd like you to post those questions. And again, it can be anonymous. That's another reason I do it. So I don't know who sends them if you check anonymous. But those are the questions that I will go through next week, and that's pretty much it. So if nobody puts a question up, there's no review unless you come that day. But I really like to come with a plan and to know what questions and stuff you have so that I can bring materials. So please, if you get a chance, at least try to jot a few things down on there so that we can come prepared, okay? Okay, so we're still out early, but I think we handled today pretty well. Y'all did good. Okay.